Welcome back to this course on the foundations of continuum mechanics. Today we'll be solving a fluid flow problem in this lecture. Let's get started. So let us discuss the problem first. So in this problem, we have an inclined surface which is inclined at an angle of beta with the horizontal, and there's some water that's flowing on this surface like this, with the top surface of the water as shown in the solid blue line having a height which is given as small h. So you can think of this as a mountain with the incline beta as the slope of the mountain, and there is some water flowing on the surface of the mountain in this case. The pressure on the top surface is P naught, which is the atmospheric pressure. And the water in this case is flowing because of a gravitational force. So this is the acceleration due to gravity vector acting in the downward direction. And since the choice of coordinate system is typically ours, it's our choice how we define our coordinates. So in this problem, it's most convenient if we choose a coordinate system which is aligned with the slope, because that's how the water is flowing. So we'll say that this direction along the slope is the coordinate small x2. And remember, we always work in spatial coordinates when working with fluids, because it's always the current configuration that's of interest, not the reference configuration. And then the coordinate which is normal to the surface will be called small x3. And with this, small x1 is the coordinate that's coming outside the plane of this sheet. So that will be called as small x1. So this dot with a circle means it's coming out of this plane. Now in this situation, we are given that the x1 direction is infinitely long. So this is our x1 direction as we just mentioned. And then we have the direction x2, which is like this. And then x3, which is normal to the surface, is something like this. So we can see that this inclination is very long in this direction. So such situations where one of the coordinates is infinitely long, we can assume that situation to be two-dimensional. That is, if you consider the flow which is happening here, which is safely much away from the boundaries, then you can assume that the flow here is completely independent of the x1 direction. So it's given to us that the flow is incompressible, which is a decent assumption for water as we discussed last time. And it's also given that the fluid is Newtonian, which is also what we discussed in constitutive modeling earlier this week. So for water, a Newtonian model is quite relevant. And it's also given that the flow is steady. So as we discussed last time, that steady means that del Vi upon del T is 0, and so is del P by del T as well. So things are not a function of time if you look at some specific position in space. So given this information in the problem, so let's call this the problem that we are solving. We are asked to find the velocity field and the pressure field. So we have to find the velocity and pressure fields in this situation. So when I say velocity field, what that means is I need to find v vector as a function of small x vector and t. But since it's a steady state situation, so we already know that v vector is not a function of time. So I can remove that. And I need to find the pressure scalar field as a function of small x vector as well. So this is what we have to find. So let's solve this problem, which will be the discussion in today's lecture. So what we are going to do is we are going to apply the ideas we have learned in this course to solve this realistic problem in fluid mechanics. So first, let us see if based on the physics or based on the symmetry of the problem, we can simplify the situation. So when I say velocity field, that means I need to find V1, V2 and V3 as function of x1, x2 and x3. And also I need to find P as a function of x1, x2 and x3. Now since we know that the situation is symmetric along the x1 direction, so that means V1 is 0 because due to symmetry, there's no reason for water to be flowing in the x1 direction. That is, it does not have any preference to flow in the positive or the negative x1 directions. So by that argument, V1 is 0. And this typically is a situation when you talk about one of the directions being infinitely long. Now, if we look at the situation, what we also see is that we don't expect water to be flowing up or down, that is perpendicular to the surface. We expect the water to be flowing along the surface, not perpendicular to it. So that's a very commonsensical argument, and from that logic we can say that V3 also is 0. That means velocity is only present in the V2 direction. So we only need to find V2 now. We have assumed V1 and V3 to be 0 in this case. So I'll say that this is from symmetry. And this is from the physics. Also, if I look at V2, now V2 in general is a function of x1, x2 and x3, but since we said that the effect of x1 coordinate is not present because of the symmetry along the x1 direction, so I can say that V2 is just a function of x2 and x3, and that is also from symmetry. So I'll just box this, that this is what we need to find now, and that will be our aim, because we've assumed that V1 and V3 are already identically 0 everywhere. And there is no simplifying assumption we apply on pressure as of now. So we keep this general in terms of x1, x2 and x3. Let us first apply the conservation of mass equation, also known as continuity. So in the Eulerian form, we wrote that the continuity is rho dot plus rho times Vk comma k is a 0. But for this situation where we're talking about incompressible flow, rho dot is a 0. So this boils down to simply Vk comma k equal to 0, which can be expanded to give V1 comma 1 plus V2 comma 2 plus V3 comma 3 is a 0. But we just saw that V1 and V3 are zeros, so these go away. So all we are left with is that V2 comma 2 is a 0. So I can write this as del V2 by del small x2 is a 0, which when integrated gives that V2 is some function purely of x3, because if V2 was a function of x2, then del V2 by del x2 could not be 0. And if I go back, we had stated here that V2 in general was a function of x2 and x3, but due to this continuity condition, we have found out that V2 actually is only a function of x3, not x2. So I can express this as V2 is purely a function of x3. So that even simplifies the situation further, that we need to find V2, which is purely a function of x3 now. Now the meaning of V2 being a function of x3 is that for this incline that we have, which is making an angle of beta with the horizontal, our velocity, where x2 direction is this and this is x3, and what we are saying is that the velocity that we have in this direction, that's v2, is only a function of x3. So if I was to plot the velocity as a function of x3 direction, then I would see that these vectors would be of different lengths as I move up or down. Now my intuition says that the bottom surface provides some sort of a resistance to the fluid, so I expect the fluid to be moving slower near the boundary, that is near the surface of the mountain, as compared to on the top, where there's no constraint or where there's no shear that is slowing the fluid down on the top surface, because that is exposed to the atmosphere. But again, that is our intuition. We haven't found the solution yet. Once we find the solution, we will find how the velocity varies as a function of x3. So all we know for now is that v2 is purely a function of x3. Now we write the momentum equation. So the momentum equation was that rho times vi dot is sigma I j comma j plus rho times bi. So that's the local form of the momentum equation, that is, it's valid at each and every point inside the fluid domain. Now the left hand side, I can expand this using the material derivative. So this becomes rho times del Vi upon del T plus Vk times Vi comma k, and the right hand side is sigma ij comma j plus rho Bi. Now this is a 0 because we know it's a steady state situation. So we are left with this equation where we have rho times Vk times Vi comma k equals sigma ij comma j plus rho Bi. So let's call this 2, and to be able to go any further, I need to figure out these terms in the equation. So let's work to find sigma ij now. Now since this is a Newtonian fluid, so we can use the constitutive model for a Newtonian fluid, which was found out as sigma ij is minus p delta ij, so that's the hydrostatic part, plus tau ij, which is twice mu times dij, where capital D is the rate of deformation tensor, minus 2/3 of mu times dkk times delta ij. Now remember, we talked about the Stokes hypothesis last time, so from that we end up reducing the number of viscosity coefficients to just 1. Now we still haven't found out dij, so we need to find that. So let's call this 3, park it here, and then proceed further to get dij. So the rate of deformation tensor dij is the symmetric part of the velocity gradient tensor. So let's first find d11, which is v1 comma 1, but we already stated in the beginning that v1 and v3 are 0, and we found out that v2 is purely a function of x3. So we'll be using these ideas to find the expression for dij tensor. So v11 is a 0 because v1 is a 0 everywhere. Then d12 is half v1 comma 2 plus v2 comma 1. Now v1 comma 2 is a 0 because v1 is 0, and v2 comma 1 is a 0 because v2 is purely a function of x3. So this also becomes 0. Then we have d13, which is defined like this. Now v13 is a 0 because v1 is 0, and v31 is a 0 because v3 is a 0. So this comes out to be 0 as well. So moving to the next row of D, then we have D21, which is half v2 comma 1 plus v1 comma 2. Now v1 comma 2 is a 0 because v1 is 0, and v2 comma 1 is a 0 because v2 is purely a function of x3. So this again is a 0. Next we have d22. Now v2 comma 2 is a 0 because v2 is purely a function of x3. This is also 0. Next we have v2 comma 3, which is half v2 comma 3 plus v3 comma 2. Now v3 comma 2 is a 0 because v3 is 0, but there's no reason for v2 comma 3 to be 0 because v2 is actually a function of x3. So this reduces to simply v2 comma 3 divided by 2. So at least we have one component which is not 0. And since D is symmetric, so we can also say that this is also D32. So next we come to D31, which is equal to D13, and we found out D13 to be 0. We just need to check for D33, but since D33 involves V3 comma 3, and since V3 is assumed to be 0, so this is a 0. So let's express our rate of deformation tensor in a matrix form now. So we found out these components to be 0 except that D23 was V2 comma 3 divided by 2. Similarly, D32 was V2 comma 3 divided by 2, and the rest of the components were 0. So this is our rate of deformation tensor. And now I can find my sigma, which was given as minus p times delta ij plus twice mu dij minus 2/3 mu times dkk times delta ij. Now we can clearly see that dkk is a 0. That's a trace of the D tensor, and the diagonal terms of D are all zeros. So all we are left with is this part. And if I express this in the matrix notation, then my sigma matrix, that's the Cauchy stress tensor, becomes, so I add a minus p to the diagonal terms. So all my diagonal terms now become a minus p because we had 0 in the D tensor. And you multiply the D tensor by twice of mu. So the 0 parts remain like this. And then the v2 comma 3 becomes mu times v2 comma 3. And since we're multiplying by 2, the factor of 2 is gone in the denominator. And we have mu times v2 comma 3 here as well. So this is our Cauchy stress tensor. So let's go back and have a look as to why we were doing all this, because in equation 2, that's the momentum equation, we needed sigma ij comma j, and since we have the Cauchy stress tensor now, we can get this. But we also need to find rho times bi. Now bi is the body force per unit mass. So in this case, our bi is simply the gravity vector. And the reason is because the force of gravity is mg, and since we're talking about force per unit mass, so bi is simply the gravity vector. Now since our incline is like this and gravity is acting along this direction, and our x2 and x3 directions are like this, so I can find my gravity vector components as the first component is a 0 because there's no g along x1 direction, and then along x2 we have a g sine beta times e2 hat, and then along x3 we have a g cos beta times E3 hat. Actually, this has to be negative because gravity is acting along the negative E3 direction. So this is our body force vector. So I'll write my momentum equation again. So that's rho times Vk times Vi comma k. That's equal to sigma ij comma j plus rho times Gi. So this has three equations here because we have one free index I. So let's apply this for I equal to 1 first. So our left hand side becomes rho Vk V1 comma k equals sigma 1j comma j plus rho G1. So let's go term by term. So on the left hand side we have a V1 comma k, but we know that V1 is a 0. So if V1 is a 0, then V1 comma k is also a 0. So the left hand side actually becomes a 0 because we have V1 equal to 0. On the right hand side, we have a G1 here, but we just found out that G is only along the E2 and E3 direction. So G1 is a 0 as well. So we are left with a very simple situation here, that is sigma 1j comma j equal to 0. And when I expand this, this becomes sigma 1 comma 1 plus sigma 1 comma 2 plus sigma 1 comma 3 is a 0. So if I look back at my sigma tensor, then I can see that sigma 1 is a minus p, but sigma 1 and sigma 1 are both zeros. So this becomes minus p comma 1 equal to 0. And that basically means del p by del x1 is a 0, which implies that p is only a function of x2 and x3. So remember, in the beginning, we did not put any condition on the pressure field, but from this first momentum equation, we get that p is not a function of x1. And that sort of was expected because the system is symmetric along the x1 direction. So like velocity, we also expect the pressure not to be dependent on the x1 direction. I'll put a red box here because this simplifies our pressure function. So let's move on to I equal to 2. Now if we expand the left hand side, we get rho V1 V2 comma 1 plus V2 V2 comma 2 plus V3 V2 comma 3, and this is equal to, we'll expand the sigma as well, so we get sigma 21 comma 1 plus sigma 22 comma 2 plus sigma 23 comma 3 plus rho G2. So now we saw that V2 is purely a function of x3, so that means these terms go away. But since we have a V3 here, so this also goes away. We can say V3 is 0, and here we can say that V2 is purely a function of x3. Now let's look at the sigma tensor again. So in the second row in the sigma tensor here, we see that sigma 21 is a 0, but sigma 22 and sigma 23 are not zeros, so they will participate in the equation. So sigma 21 comma 1 will be a 0 because sigma 21 is a 0, but the others are not. So we finally get a 0 equals, now sigma 22 was a minus p, so we get a minus p comma 2 plus, and sigma 23 was a mu times v2 comma 3, this comma 3. Then we have rho times g2, and g2 was given as g sine beta. So we get a g sine beta. So the overall equation we get is minus p comma 2 plus, now we assume that mu is homogeneous, so we get mu times v2 comma 33 plus rho g sine beta is a 0. So let's put this in a box as well. because we'll be using this soon. Finally, we use I equal to 3 case, which is rho times Vk times V3 comma k equals sigma 3j comma j plus rho G3. So let's expand the left hand side. So we have rho times V1 times V3 comma 1 plus V2 times V3 comma 2 plus V3 times V3 comma 3. On the right hand side, we have sigma 31 comma 1 plus sigma 32 comma 2 plus sigma 33 comma 3 plus rho G3. So V3 is a 0. So all these terms go to 0. And then let's look at the sigma tensor again. So in the sigma tensor, the last row, which is sigma 3 1 is a 0, but sigma 3 2 and sigma 3 3 are non-zeros. So we get the condition where we have a 0 on the left hand side. Sigma 3 1 is a 0, so this also is a 0. So sigma 3 2 was mu times v2 comma 3. So we get a v2 comma 3 2 here, plus now sigma 3 3 was a minus p. So we get a minus p comma 3 plus rho times G3. Now G3, if you recall, was a minus G cos beta. So we have a minus here. Let's look at this term. So this is V2 comma 3 2, which can be written as V2 comma 2 whole comma 3. And V2 comma 2 was a 0. That's what we saw from the continuity equation. So this is also 0. So ultimately we are left with an equation where we have p comma 3 plus rho g cos beta is a 0. So we'll put this in a box as well. And I'll label these now. So this we'll call C. And the condition we got from the I equal to 2 was, we'll call B. So first I'll integrate equation C. So we have a p comma 3, that is we have a del p by del x3 equals minus rho g cos beta. So all I need to do is I need to integrate this with respect to del x3, and then we have a constant here as well. But since we are doing this partial integration, so this constant will be a function of x1 and x2. So I can write my p as minus rho g cos beta times x3, because rho g and beta all are independent of spatial coordinates, plus some function c of x1 and x2. Now we already saw that pressure is not a function of x1, so this constant cannot be a function of x1, so this is only a function of x2. The last time we discussed that we need some boundary conditions to get the constants of integration. So the condition that was given to us for pressure was that pressure is P naught at x3 equals h. So that was a given as a boundary condition. So if I substitute that in this equation, because this is a general function that we found out, it should also satisfy this boundary condition. So we get P as minus rho g cos beta times h plus C as a function of x2, and this pressure has to be equal to P naught. So this allows us to get C as a function of x2 as P naught plus rho g cos beta h. So actually C is not a function of x2 at all. So therefore our pressure general is minus rho g cos beta times x3 plus, and then C is P naught plus rho g cos beta times h. And I can write this in a more convenient form as P naught plus rho g cos beta times h minus x3. So we have found out the pressure as a function of spatial coordinates. In this case, it's only a function of x3. So we should put a double box here because that was one of the things we had to find out. Now, if we see equation number B here, we will integrate this for getting the velocity field. So I'll rewrite equation B, which was minus p comma 2 plus mu v2 comma 33 plus rho g sine beta equal to 0. But we just saw that pressure is only a function of x3, so p comma 2 becomes a 0 because purely p is a function of x3. So we have mu times del 2v2 upon del x3 squared plus rho g sine beta is a 0. So if I integrate this twice, for the first time we'll get minus rho g upon mu times sine beta times x3 plus some constant which is a function of x1 and x2. But we already have established the fact that our v2 is a function of purely x3. So this is just a constant. Let's call this a. So that's v2 comma 3. But if I integrate this again, then I'll get v2. But then this becomes x3 squared upon 2. We get an x3 here and we get another constant b. So this is a function of x3. So now we apply boundary conditions for velocity. So the first boundary condition we'll apply is something that's called a no-slip boundary condition. That is, the velocity v2 at x3 equals 0 is a 0. So this slope that we had, where we had water above it, at this bottom point, the water molecules which are contacting this solid inclined surface, they stay stationary. That is what this no slip condition means. So let's substitute that. The expression for v2 as a function of x3. So from this, we see that we have b equal to 0. So that helps us get one of the constants. Now we need one more boundary condition to get the another constant of integration. And the other boundary condition we have is on the top of the surface of water, and this condition is called free shear. I'll write the boundary condition as free shear on x3 equal to h. That means sigma 3(1) equal to sigma 3(2) equal to 0. And since sigma 3(2) was mu times v2 comma 3, so that is a 0. So that basically means that v2 comma 3 is a 0. And if you look at this function, if I differentiate that with respect to 3, so we get v2 comma 3 as minus rho g upon mu times sine beta times x3 plus a. So this is a 0 at x3 equal to h. So we have a minus rho g upon mu times sine beta times h plus a equal to 0. So this was important, it's at x3 equal to h. And from here, we get the constant a as rho g upon mu times sine beta times h. So therefore, our velocity v2 as a function of x3 finally becomes rho g sine beta upon twice of mu times twice of h minus x3 times an x3. So it's a parabolic velocity profile. So if I was to plot this on the surface, So what I would see is that on the surface, the velocity v2 component is a 0, and as I go up, it parabolically increases. That is, it quadratically increases. And on the top surface, that's at a height of h, we found that v2 comma 3 is a 0. So that means that this function becomes flat on the top surface. So I'll put a box here, in fact a double box, because this is what we had to find. So we have successfully solved the problem because we were able to find the velocity and pressure fields for this flow situation. So this was a successful demonstration of solving a realistic fluid mechanics problem using the ideas that we have learned as a part of this course. So we feel ready now to be able to jump into advanced subjects and apply the foundations of continuum mechanics that we have learned in this course. So thank you and see you next time.